Okay, in this video we're going to look at rational functions. So rational functions come in this form. So f of x is the function, and you have a numerator, and then you have a denominator. Okay, so rational numbers are fractions, or numbers that can be written as fractions. Rational functions are functions that can be written as fractions. So a function divided by another function. And for the ones that we're going to be looking at for this section, it's going to be a polynomial over a polynomial. So we're not going to do, at this point, sine of x over log of x or anything. This is going to be a polynomial over a polynomial. Okay, and the first type of rational function that we're going to look at are reciprocal functions. So reciprocal functions are functions where the denominator is a polynomial and the numerator is just 1. Okay, so reciprocal functions are ones that look like this. F of x equals 1 over some denominator. Okay, so the most simple reciprocal function is this one. F of x equals 1 over x. We're going to be looking at graphing these. Okay, so 1 over x looks like this. Okay, so you got x and y axis. And so you've got 1 over x. If you take all the numbers that are positive on this side and you do 1 divided by those numbers, well, 1 divided by a really small number between 0 and 1 is going to be big. And 1 divided by a really big number, say greater than 100, is going to be really small. It's going to be 1/100th. So this side of the graph looks like that. Okay, and where the sharpest point here is at 1 and 1. Now on the other side, where it's negative, well, you're dividing 1 by negative numbers. It's going to have the same effect, but when you divide a positive and a negative, you get a negative, so you end up with this function here. Okay, and again, that point there would be at -1 here and -1 there. So that's what 1 over x looks like. If we wanted to look at 1 over any linear function, well, let's look at another example here. So let's look at, so here's one example. Let's look at another one. Let's say f of x in this case equals 1 over x minus 2, for instance. Well, in this case, if you look at this, there is nothing at x equal to 0. And if you think of why, well, you cannot divide by 0. So because you cannot divide by 0, then there is no value, there is no y value for this function when x equals 0. So if you look at the domain for this function, its x is all real numbers except for 0. So what we have here is what's called a vertical. So the y-axis ends up becoming a vertical asymptote. Okay. Now an asymptote is, well, vertical asymptote is a line that the function never crosses, but it comes very close to. And you could give me a distance that it comes close to, that it has between that asymptote and the function, and it'll come closer than that, but it'll never touch. The reason it cannot cross a vertical asymptote is because it wouldn't be a function then. Okay, so if the function happened to come across here and then start approaching it, well, it wouldn't be a function because it wouldn't pass the vertical line test. And more importantly, there may be places where there's more than one y value for every x. So if we remember the definition of a function, so if this is the vertical asymptote and it comes across it and then goes like this, well, at this x value here, there's more than one y value. Okay, so that is not a possible function. This is why a function cannot cross a vertical asymptote. A function can cross an asymptote that is horizontal, though, or an asymptote that is diagonal, and we'll see that in the future. Okay, so it cannot cross a vertical asymptote, but the function can cross any other asymptote and still remain a function. So for this one here, well, if we look at it, for all x values that are greater than 2, the denominator is positive. All x values that are less than 2, for example 1 minus 2 is negative 1, so all x values that are less than 2 become negative. So what this x minus 2 does on the bottom is it just shifts this thing to the right, and you end up getting this function here where you've got x, y, and here's 2, say. So you put in the line x equals 2, and now you're just shifting this function to the right, so you're getting this type of an effect, and it looks like that. Okay, same type of shape, just shift it over. Now, same thing if it's f of x equals 1 over 3x plus 5. Well, that's going to look similar to this, except you want to find out what values of x make this 0, so you know where the vertical asymptote is. So this one, it was at x equal to 2. Okay, you can't divide by 0, so x cannot be 2. Well, what value would make the bottom 0 here? Well, if you put in negative 5 over 3, okay, the 3's cancel out, then the negative 5 plus 5 becomes 0. So it's always going to be the opposite sign of this, and then this over this, okay, if you know how to solve linear equations. So the vertical asymptote at this one is at, so basically x cannot equal negative 5 over 3, so the vertical asymptote is at negative 5 over 3. Okay. You can also write this function as 1 over 3 times x plus 5 over 3. So you could factor a 3 out of the whole thing on the bottom. Okay, and then that becomes a stretch factor, and that becomes a translation to the left, 5 over 3. So basically, this function, for our purposes, okay, labeling the axes all the time, it's like punctuating sentences. Okay, so this is going to move to the left because at x equals to negative 5 over 3, which is almost at negative 2, that's going to be the vertical asymptote, and it looks like this. And you put in a little label here, x equals negative 5 over 3. Okay. Now, if that happened to be a negative 1 on top, or there's a negative on the bottom in there in front of the x, then it would just be flipped over. Okay, it'd be a vertical flip. So that is reciprocal functions for linear functions. And if you